Hello, welcome back to the NPTEL online certification course on deep learning. For last few lectures, we are discussing about various techniques for improvement of gradient descent algorithm, where gradient descent algorithm is nothing but the algorithm of training of the neural network or deep neural network that we are talking about. So far we have discussed about the momentum optimization technique, which optimizes the gradient descent algorithm. We have also talked about the Nesterov accelerated gradient based optimization technique, and we have also talked about the AdaGrad. So in our previous class we have talked about the AdaGrad algorithm in particular. So in today's class we will talk about two more algorithms. One of them is RMSProp and the other one is ADAM, and we will also see a very closely related algorithm which is very closely related to RMSProp. So as we have seen in the previous class, the AdaGrad algorithm is given something like this, that at time t you compute the batch gradient of the loss function with respect to the weight vector or with respect to the parameter vector. And then what you do is you go on accumulating the squared gradient, or you take the sum of squared gradient of all the historical gradient values. And this sum of squared gradient is used to scale the gradient of all individual locations. So as a result, our upgradation or weight upgradation algorithm that we have seen earlier is given by this expression, where if Wt is the parameter vector or weight vector at time t, then at time t plus 1 we get our updated weight vector as Wt minus eta upon square root of epsilon I plus Rt times Gt, where these operations are actually done element wise. That means whenever I write 1 over square root of epsilon I plus Rt, so for individual components this will actually be 1 over square root of epsilon plus Rt I. So this is the sum of the squared gradient, sum of the squares of the ith component of the gradient vector, and you take the square root of this, and times gt, that means this will be multiplied by corresponding ith component of the gradient gt, and that will be added with the ith component of Wt. So in fact your expression will be that if I go for component wise, Wt plus 1 ith component will get Wt ith component of this minus eta by square root of epsilon plus Rt I times Gt I. So this is the component wise operation that you perform, and here you find that you are basically scaling the ith component of the gradient vector by square root of sum of squares of the corresponding component of the gradient vector, and where you are taking the summation over all the previous the gradient values or the partial derivative values that has been computed. So this is sum of all the historical values, and this is what is actually scaling the ith component of the gradient vector, which effectively is updating the ith component of the weight vector or the parameter vector. So what is the effect of the scaling is that if for certain component, say for Wi, you find that del L del Wi, which is nothing but our GTI. So if this del L del Wi is very large, then this corresponding RTI will also be very large. So as a result, 1 upon square root of RTI, which will be small, and that is making your learning rate of the corresponding ith component of the parameter to be small. And if this is small, RTI is small, and then the corresponding learning rate of the ith component of the parameter vector will also be large. So this is how AdaGrad algorithm is adaptively tuning the learning rate of individual parameters or individual weight components of the weight vector. So we have also seen that what are the positive points of this AdaGrad algorithm. So the first positive point is it adaptively scales the learning rate for different dimensions by normalizing with respect to the gradient magnitude in the corresponding direction. So if the gradient magnitude in a particular direction is more, the learning rate in that direction will reduce, whereas if the gradient component in a particular direction is small, the learning rate in that particular direction will not reduce that much. So that is how you adaptively tune the learning rate in different directions. And you don't have to manually set any of the hyperparameters, though initially we have the initial learning rate given by eta, but once we fix, that is final. We need not update it anymore. And as a result, the learning rate becomes faster and you quickly converge to the to the minima of the error function. So these are the positive points of the AdaGrad algorithm. And the negative point is, if the function is non-convex, which is quite possible given your high dimensional space in which the error function is defined, then while the algorithm proceeds, the trajectory of the weight vector or the parameter vector may pass through many complex terrains before coming to a locally convex region. So the moment it comes to locally convex region, we want that the algorithm will quickly converge to the minima of this locally convex region. But because the learning rate is being gradually reduced, it is being scaled by square root of the sum of the squares of the corresponding partial derivative, and this summation is taken from t equal to 0. It is actually accumulative, and this being sum of the squares, it always goes on increasing, it does not reduce at all. So as number of iterations proceeds, your scaling factor, that is 1 upon square root of epsilon plus r, that will go on increasing, and as a result your learning rate may become very small with time, and in some cases the machine may stop learning at all. So that is the problem of AdaGrad algorithm. So let us see that how the other suggested algorithms take care of or try to solve this problem which is given by AdaGrad. So the algorithm that we'll talk about is what is RMSProp, which tries to address this problem of AdaGrad algorithm, that is vanishing learning rate as the time increases, as the number of iteration proceeds. So what this RMSProp algorithm does is, instead of taking the accumulative sum of squares of the gradients of the sum of the squares of the past gradients, where this past gradient starts from time t equal to 0. Okay. So you are basically, the operation that was done in AdaGrad algorithm is RT, the scaling factor, which is 1 upon square root of epsilon plus RTI. So if you go for component wise, this RTI is nothing but sum of GTI square of this, or let me put it as G tau square instead of GT, G tau square, and you take the summation of tau is equal to say 1 to t. So you find that this being a square term and which you are going on adding, so RT goes on increasing, it monotonically increases with t, it does not reduce. So that is the problem with the AdaGrad algorithm. And in case of RMSProp, instead of using this cumulative or accumulative sum of squared gradients, the RMSProp takes exponentially decaying average of the squared gradient. and it does not consider the extreme past histories while accumulating the sum of squared gradient. And as a result of this, the algorithm converges rapidly once it reaches, once your vector reaches a locally convex ball short of surface on the error terrain. And what you can do is we can assume this point, once it reaches that locally convex error surface, that as if your AdaGrad algorithm is initialized at that point within that locally convex ball. So that is what the RMSProp does. RMSProp does not take the accumulative sum of squared gradients from the very beginning, but it takes an exponentially decaying average of squared gradient. Now let us see that what is this exponentially decaying squared gradient. It is something like this. Suppose we have a sequence of numbers or sequence of samples given by say S1, S2, S3, S4, it goes on Si, Si plus 1, and it goes on like this. So it goes on with time t. So the exponentially decaying average is defined like this. I want to define say Vt at time instant t, which is the exponentially decaying average. This will be same as beta times Vt minus 1, where Vt minus 1 was the exponentially decaying average at time t minus 1, plus 1 minus beta times St. And this is initialized to say V0 is equal to 0. So you start with this initialization. So once I initialize V0 is equal to 0, that means V1 will be beta times V0 plus S1, and because plus 1 minus beta times S1. So because V0 is equal to 0, so effectively you get V1 is equal to 1 minus beta times S1. At time t equal to 2, I get V2, which is nothing but beta times V1 plus 1 minus beta times S2. And this V1 is nothing but 1 minus beta times S1. So this will simply be 1 beta into 1 minus beta times S1 plus 1 minus beta times S2. Similarly, V3 will be beta times V2 plus 1 minus beta times S3. So you find that in this term beta times Vt minus 1, this term is weighted. I mean, I have an weighting component which is beta into beta square into beta cube and so on, and then beta is actually less than 1. And typical value of beta is taken to be 0.9. So 1 minus beta will be 0.1. So all the previous sample values, as I compared say S50, the previous sample values, the effect of S1, S2, S3 and so on, that will go on reducing exponentially. And that is the advantage of taking the exponentially decaying average of the square gradients. And this is what is used in case of RMSProp. So in case of RMSProp, the scaling factor is not the cumulative sum of gradient histories, but it is the exponentially decaying average of the squared gradients. So if I go to the updation algorithm using RMSProp, the updation algorithm will be like this. You find that you compute the gradient in the same way as we have done in case of AdaGrad. So this is the gradient computed over a batch, and Then in order to compute RT, this is not the sum of the previous squared gradients, but it is an exponentially decaying average of the squared gradients. Okay. So, this GT into GT, this gives you the squared gradient, which is initialized to 0. So, this expression that RT is equal to beta times RT plus 1 into 1 minus beta times GT into GT, this gives you the exponentially decaying average of GT square. And then your update algorithm, that is WT, is equal to, or WT plus 1 is equal to WT minus eta by square root of epsilon plus 1 epsilon I plus RT times GT. This algorithm remains the same as in case of AdaDelta. So, only difference is this RT is not the cumulative sum of squared gradients, but this RT is the exponentially decaying average of the squared gradients. And we said that there is a very closely related algorithm, very closely related to this RMSProp. So, that closely related algorithm is what is known as AdaDelta. So, we have a closely related algorithm known as AdaDelta. So, what AdaDelta does is, in case of RMSProp, you are taking the exponentially decaying average of the squared gradient. AdaDelta, instead of taking the exponentially decaying average of squared gradient, it computes the moving window average. So, you can take a window size of say W. So, when you compute VT, VT is computed over a past window size of W. So, if I take say window size W is equal to say 5, in that case, in order to compute say V10, it will take the past 5, that means it will take V10, V9, V8, V7 and V6, or say S6, S7, S8, S9 and S10. So, the average will be computed over this window of 7. Similarly, when you compute, so this is what is your V10. When you compute V11, I have S11, which is the next sample. The average will be taken over S7, S8, S9, S10 and S11. That will give you the average of V11. So, you are computing average over past samples which are within this window size of W. So, this is what is moving window average. So, you find that this RMSProp, which takes exponentially decaying average, the AdaDelta takes a moving window average of the squared gradients. So, that is the only difference between RMSProp and AdaDelta. And in fact, both these algorithms were proposed almost simultaneously, but independently. And both of them gives almost similar performance. So, this is what is your RMSProp algorithm. You can also improvise upon RMSProp algorithm with Nesterov momentum term. So, as we have seen that in case of Nesterov accelerated gradient technique, you take the gradient not at location WT, but you take the gradient at a look ahead position. So, assuming that your previous momentum term is V, you are looking ahead at location WT plus alpha times V, and you are taking the gradient at that location WT plus alpha times V instead of computing the gradient at location WT. So, that is what your Nesterov accelerated gradient is. So, you instead of computing the gradient at location WT, if I take the gradient at location W tilde, where W tilde is the position or look ahead position, and rest of the algorithms remains the same. So, it is as before, you are taking the exponentially decaying average of the sum of squared gradients, exponentially decaying average of the squared gradients, and then your update rule remains as before. Okay. So, this is what is RMSProp, which is further improvised with Nesterov momentum. So, given this algorithm, now the other algorithm that we said that we will be talking about is what is known as ADAM or adaptive moments. So, what is this ADAM algorithm? ADAM algorithm, you can consider this to be a variant of the combination of RMSProp and momentum. So, in case of RMSProp, we did not have any concept of momentum. So, here we can incorporate both the first order momentum and the second order momentum. Second order momentum is nothing but the sum of squared gradients or exponentially decaying average of the squared gradients, as in case of RMSProp, which is used for scaling the learning rate in individual directions. And along with that, if we add the momentum term, where the momentum will be scaled according to the square root of the exponentially decaying average. So, if I use both this first order momentum and second order momentum, because sum of squared gradients is nothing but, or average of the squared gradients is nothing but equivalent to your second order momentum. So, you use both this first order and second order moment, that becomes a variant of RMSProp, and this is what is known as ADAM. So, in case of ADAM, you are including both first and second moments for weight updation or parameter updation. And in addition, ADAM incorporates one more term, that it tries to correct the bias to account for initialization to 0. So, what we said is that when you are taking exponentially decaying average, you are initializing the average value at 0 at t equal to 0, right. So, for this exponentially weighting average, what we did is we have computed Vt is equal to some beta times Vt minus 1 plus 1 minus beta times St. So, when you go for exponentially decaying average of the squared gradients, this St is nothing but your gradient del L del W square of this. So, here what we are doing is you initialize V0 to 0. So, as a result, all the computations that you are performing, particularly the computations at the initial sample levels, t equal to 1, t equal to 2 and t equal to 3 and so on, all of them are actually biased towards 0. So, in order to avoid this bias, what this ADAM algorithm does is it goes for correction of the bias term, and the correction is done by dividing the computed values or the exponentially decaying average values by 1 minus beta. So, the operation is something like this. So, as before, you compute the gradient over a batch at time t, which is gt. Then you compute the first and or exponentially decaying average of the first and second moment of gt. So, the exponentially decaying average of the first moment of gt is given by St is equal to some beta 1 times St minus 1 plus 1 minus beta 1 times gt, and the second moment exponentially decaying average of that is given by Rt is equal to some beta 2 times Rt minus 1 plus 1 minus beta 2 times gt square, which in this case is written as gt into gt. We have said that this particular symbol small square, this is used to represent element wise multiplication. And as we said before, that this exponentially decaying average that we have computed, it is biased towards 0, because at t equal to 0, both St and Rt, that is S0 and R0, are initialized to 0. So, in order to take care of this bias, the Adam algorithm goes for bias correction, and for bias correction it takes ST hat, which is the bias corrected first moment, which is ST upon 1 minus beta minus 1 upon 1 minus beta 1, okay, where the computation was ST like this. ST was beta 1 times ST minus 1 plus 1 minus beta 1 times ST. So after correction, it becomes ST upon 1 minus beta 1. So this corrected first moment is represented as ST hat. Similarly, the corrected second moment, which is RT hat, is nothing but RT by 1 minus beta 2. So once given this, your weight updation of the parameter updation rule simply becomes WT plus 1 is equal to WT minus eta times ST hat, where ST hat is the bias corrected first moment, upon square root of epsilon I plus RT hat, where RT hat is the bias corrected second moment. So you find that this is nothing but similar to your RMSProp algorithm, where you are incorporating, where this Adam algorithm incorporates bias correction operation, and it also incorporates the first moment in the update step. So this is eta times ST hat, where ST hat is the first moment of the gradients. So this is your Adam optimizer, which optimizes the gradient descent operation. So now we can compare with this animation. You can see that I can compare the relative performance of different optimization algorithms. So as you see over here, this rate curve, the rate curve is actually the pure SGD algorithm or stochastic gradient algorithm. The blue one gives you the momentum. Then you have NAG, Nesterov accelerated gradient operation. Then you have AdaGrad. Then you have AdaDelta. Then you have RMSProp. So you find over here that the SGD, which you find that it is still converging, whereas the other algorithms have already converged. And as we have seen before, that your momentum and the NAG, as we said, that NAG, that is Nesterov accelerated gradient, gives slight improvement over momentum, right? So you find that these two, green and the pink one, they represent momentum and NAG optimization, and they are very close. So we have discussed about the various optimization techniques, where this optimization techniques tries to improve the learning rate given by gradient descent algorithm. So we'll stop here today, and we'll talk about how the other challenges that you get in gradient descent or the learning algorithms of deep neural networks are addressed by different approaches in our future lectures. Thank you.